Morning class, and here I am with the next component of the circuit, that is battery eliminator. Battery eliminator is a device which bypasses the requirement of the battery. You can see here is a knob which gives us different voltages as we require in a particular experiment. We are having two other knobs here. See, two other knobs. This is the red one. Can you see the color of the knob? It's a red color knob, and this is black color knob. The red color knob is positive terminal of the battery and black color is negative terminal of the battery. So for the outer appearance, the structure is simple. If you switch on, then power is on. I have not connected it with the switch, so we don't have the indicator here, but this is to switch the power on, right? And for the inside brief structure, you don't need to know it much, but a brief structure that actually what is happening inside this battery eliminator. So let me quickly get this information. But a battery eliminator, as I told you, is a device which allows us to bypass the use of battery, and it provides DC power at different voltages, right? Now it has following parts. The first part is there is a step down transformer inside it. Why? Because when you connect it with the AC mains, we have 220 volt AC. Now this transformer brings the 220 volt down to the 12 to 18 volt of the voltage inside this battery eliminator. The next step, the next component inside this battery eliminator box is full wave rectifier. This is in your syllabus of your board, and in the mains and NEET also we will learn it in semiconductor. This rectifier is a device which converts the AC into DC. Then we have inside this battery eliminator a capacitor. After electrostatics we will study capacitor also. So during that lecture you will come to know what is the purpose of capacitor and how it works. But here capacitor converts the fluctuating DC. What is fluctuating DC? Fluctuating DC you will come to know in semiconductors when you will study the rectifier. But let me tell you briefly that when AC enters the rectifier, it has waveform like this. The positive as well as negative cycles all are present. But when this input enters the rectifier, all the negative cycles are eliminated and we have just positive cycles. Now what is this? This is voltage and this is time. So voltage is fluctuating with time, you can see. So after rectifier we are having fluctuating voltage. Now do you want your experiment with this fluctuating voltage, 0 to maximum value, then 0, then maximum, then 0? No, we don't want. So this capacitor is used to smooth this waveform. After that we have the next component inside this battery eliminator, voltage regulator. Voltage regulator is also Zener voltage regulator is in our syllabus and we will study in semiconductor. But here just know that voltage regulator which is placed at your fridge, its work is to maintain a particular voltage across the device fridge. The same way in our experiment this device maintains the constant DC voltage to our resistance. Next is the rotatory switch. I have shown you that we are having a switch here, the rotatory switch here, and this switch is rotated on this scale, and thus we can change 2 to 4 volt, 6 volt and up to 12 volt as we require. So next is rotatory switch. This rotatory switch is actually connected with the set of resistances. The set of resistances which is connected with the rotatory switch, they decide whether we are getting 2 volt output or we are getting 4 volt output. So just keep it in mind. Then there are set of resistances. There is a set of resistance, and that set of resistance gives output of 2, 4, 6, 8, 10 or 12 volt when we rotate the rotatory switch. And then there is a beta heat sink. You know that 220 volt comes down to 12 to 18 volt with help of step down transformer. And after say 18 volt, now if we need 2 volt output, then where that remaining 10 volt will go? That electrical energy will appear in the form of heat. So we need something which dissipates that heat produced. Otherwise our circuit inside the battery eliminator will get damaged. So we are having a heat sink. And after that we again have one more capacitor. This capacitor finally, before giving out the final output, smooths if any fluctuation is remained in the signal or the voltage we are getting out. So this is a simple brief explanation of the battery eliminator, and here we are having a transformer which steps down the voltage, and we are having AC voltage after this transformer. This AC voltage is input in the rectifier. This is known as full wave bridge rectifier, from where this AC voltage, all negative cycles are eliminated and they are converted into positive cycle. So we are having a fluctuating DC. This fluctuating DC is further passed through a capacitor. This capacitor smooths the fluctuating DC signal. Getting it? And then this DC signal is input in voltage regulator. This voltage regulator also performs two functions. It smooths further the signal, and also it maintains a constant voltage which we require 2 or 4 or 6 across this next capacitor. And this capacitor finally, before giving out us the DC voltage, smooths further our signal so that there is no fluctuation at all to the DC which we are getting out of the battery eliminator. And here are the resistances. These resistances, if rotatory knob is set to this resistance, the output we are getting from battery eliminator will be 2 volt, and so on. We are having different voltages provided by the battery eliminator. So there is a simple and as simple as possible the explanation of the battery eliminator, what is inside the battery eliminator. Now let we next come to the interesting one, that is this resistance. This is called standard resistance, beta. This resistance is called standard resistance, and it is made of constantan or magnin. Now what does it mean by the standard resistance? Standard resistance means we require a material which we can use in the lab to offer resistance in the path of the current and to perform some experiments. But this resistance should have certain properties so that it can be used in the form of standard resistance. So let me see what properties do we need in a material to use it as standard resistance, and this topic is very, very important for your competitive exams as well as for your board exam. Standard resistances, all those standard resistances are made of this carbon. Nowadays we use normally the carbon, but in the lab still somewhere we use the constantan or magnin wire. So why we use constantan or magnin wire or material? Because these materials have high specific resistance. The specific resistance of the material, this is object of experiment many times in your board practical exam. So just look at the values here. Specific resistance of constantan material is 49 into 10 to the power minus 8 ohm meter, and magnin wire is 48.2 into 10 to the power minus 8 ohm meter. So we should know these values because we have to find the specific resistance in our board exam. Then after getting this point that high specific resistance is first property which they should satisfy, the low temperature coefficient of resistance. What does it mean? That if temperature increases during the experiment, the resistance wire's resistance should not change, because you know that if temperature of a resistance increases, then resistance also increases. But see here, if 1 degree Celsius temperature is increased, then change in resistance for constantan is 0.00003 ohm, and similarly for magnin is 0.00002 ohm per degree Celsius. So that is why this is the second requirement for the standard resistance material. Although again I tell you that we now use carbon resistors. Then also, like in our lab, we use the constantan wire or magnin wire as the standard resistance. The third property which they should have high melting point, because if temperature increases, then they should be able to bear that high temperature during the experiment. Correct? Now let me move to the next material, element or component of the circuit, that is ammeter. Now here comes the important topic, because beta, many times children are not able to read the ammeter. So first I am going to explain you how to read the ammeter. Let me look at the ammeter scale. Look at the ammeter scale. What are you observing? This is 0 and this is 0.25 ampere. Between 0 and 0.25 ampere, just count how many lines we are having. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can I say that the value 0.25 ampere, change of 0 to 0.25 ampere is divided in 10 parts in the scale? 10 parts on the scale, beta. So let me see. First thing which we have to calculate, the least count of the ammeter we are using. If we calculate least count, then only we will be able to read the reading of the ammeter. So what we are looking at our ammeter, we see 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. And what we have on the 10th line? 0.25 ampere. Right? That is what we have seen. So what we will write? 10 divisions are equal to how much? 0.25 ampere. Now tell me, are you getting this concept? That 10 equal divisions equal to 0.25 ampere, or we can say 0.25 ampere value on the scale is divided in 10 equal parts. So 10 divisions is equal to 0.25 ampere. So 1 division is equal to 0.25 upon 10, that is 0.025 ampere. Got this point? Now just note down how to calculate least count of ammeter, because when we will perform the experiment, then I am going to explain you that how to take reading of the ammeter. This is very important, children, because so many students take the incorrect reading from the ammeter. The same way we are having voltmeter here. In the voltmeter, just look at the voltmeter I am having in my hand between 0 to 0.5. Look at 0 to 0.5 voltage. We are having 10 lines. Can you count? Between 0 to 0.5 volt, we are having 10 equal divisions. So least count of voltmeter we are going to calculate in the same way as we have calculated least count of ammeter. So let me calculate least count of voltmeter. Here is least count of voltmeter. In the voltmeter again we are having 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what we are having there? 0.5 volt. So as we have done with the ammeter, 10 equal divisions are equal to 0.5 volt. Right? So 1 division is equal to 0.5 upon 10 volts, which in turn will give us 0.05 volt. So least count of the ammeter we just observed is 0.025 ampere, and least count of the voltmeter we just observed is 0.05 volt. Now if I give you a homework that find least count of the ammeter here. Let me focus it. Yes. Least count of this ammeter. Here between 0 to 0.2 ampere, how many lines are there? 10 lines. So 10 divisions are equal to 0.2 ampere here. So 1 division will be equal to 0.2 upon 10 ampere. And beta, whatever is the value of 1 division of the device, that is the least measurement a device can take. You know the concept of least count, like what we are doing here in the second ammeter. First you note down the calculation we did just now, and then let me show you the least count of the second ammeter. Here 10 divisions are equal to 0.2 ampere. This implies that 1 division will be equal to 0.2 upon 10, that is 0.02 ampere. Whatever is the value of 1 division of an instrument, that is the least measurement that instrument can measure, and that least measurement is called least count of that device. That is why every time we calculated the value of 1 division of that instrument. So now here the second ammeter has least count 0.02 ampere. So now today we have discussed enough. This is all for today. In the next experiment, in the next class, actually we will set up the circuit and we will find how to take reading of ammeter and voltmeter. So till then, keep learning. Physics is fun. So please give me your feedback whether this class was useful for you or not by pressing the like button.